Hi, this is Tim Hsu from San Jose State University, and I'm here to talk about exponential growth and decay. I'll start by introducing the differential equation of exponential growth and decay, talk about some applications of growth and decay, and one variant on growth and decay, which is Newton's law of cooling. And then for those of you hardy souls who really want to understand what the magic solution I'm going to give you comes from, I'll present an epilogue which will justify the uniqueness of the solutions to the exponential growth and decay equation. Okay, so here's the problem that we're trying to solve. So suppose we want to find out some function y of t such that dy dt is equal to y prime of t equals ky for some constant k not equal to 0. So this kind of equation that we see over here is called the differential equation because it's an equation that relates y and its derivatives and other functions, and the goal in that equation is to solve for the sort of unknown function y. So what is the solution to that? Fortunately, there actually is a sort of nice solution in all cases. The solutions of the above differential equation, of this equation over here, the differential equation of exponential growth and decay, are precisely the functions of the form y of t equals c times e to the kt, where c is equal to y of 0, the initial value of y, so that's the constant c up here, and this constant k over here is the constant k that actually shows up in the equation itself. Okay, so here's one application of that solution to a differential equation. So if p of t is the size of some population at time t, then 1 over p times dp dt is the relative growth rate of p. It's the sort of a rate of change of p as a proportion of your population. And having a constant relative growth rate k greater than 0 means that precisely that 1 over p times dp dt is equal to k. Or, if we now solve for dp dt and put the p on the other side, dp dt equals kp. Hey, that's the thing we happen to know how to solve, remember? And there it is. So we happen to know that if you have dy dt equals constant times y, then y is equal to constant times e to the kt. And so similarly here, since we know that dp dt is equal to constant k times p, that means that p of t must be equal to some constant c times e to the kt, where that constant c is equal to p of 0 is the population at time t equals 0. Right, so from the mathematical fact that we saw before, that theorem, we know that that must be the case. Here's another application, so for which we first need to talk a little bit about science. So here's a scientific fact. Radioactive material decays over time to become less radioactive material or non-radioactive material. And so if m of t, to be precise, is the amount of some radioactive material at time t, then minus 1 over n times dm dt is the relative decay rate of m. And so you might be wondering, why is there a minus sign here? Why bother when you just going to have some constant anyway later on? Well, the point is that, let's see, so if m is decreasing, then dm dt is negative, and so you need to have this minus sign out front in order to talk about positive quantity being the relative decay rate. Anyway, experimental evidence shows that the relative decay rate of radioactive materials is constant, or at least it's pretty close to constant, and so we get that 1 over m dm dt is equal to a constant k, where here, remember, so the relative decay rate is positive, but when we put the minus sign over the other side, we get a constant k that's negative. So 1 over m dm dt is equal to some negative constant k. Or in other words, if you remember from our, in other words, solving for dm dt, we see that dm dt is equal to k times m. Well, that just happens to be the thing that we know how to solve again. And so m of t is equal to c times e to the kt, where c equals m of 0 is the amount of material at time t equals 0. So again, we have two very kind of different situations. There's population growth with a constant relative growth rate and radioactive decay, and they both have the same solution, a solution of the form c times e to the kt. All right, so here's one more variation, Newton's law of cooling, which may look a little bit different at first, but pretty soon you'll see is basically the same, mathematically the same problem. So suppose you have a warm object in a cooler room, and that warm object has temperature T, capital T of T, and the surrounding room has sort of room temperature T sub s, so S is for surrounding. Well, Newton's law of cooling says that the rate of cooling of the object is proportional to T minus T sub s. In other words, dt, I know that's a terrible thing to say out loud, but d capital T, d little t, is equal to a constant times T minus T sub s, where the constant k is less than 0. And I want you to think about why it must be that k is negative, because, right, so let's say a warm object in a cold room should get cooler, and so try to think through it yourself and to figure out why it is that k must be negative. Anyway, it is. So here we are. Now here's the thing we're trying to solve. D capital T dt is equal to k times capital T minus capital T sub s, where k is a negative number. Now that isn't exactly what we had before, but if we let y of t be capital T of t minus t sub s, then dy dt is equal to d capital T d little t, right? Because when we take the derivative of y, this constant t sub s goes away, and so we see that what this equation over here becomes dy dt is equal to ky, the thing that we can solve, and which means that y is equal to c e to the kt, some constant c times e to the kt, or in other words, capital T of little t is equal to t sub s plus c e to the kt. Note that since k is negative, k is less than 0, the difference between the temperature of your object and the sort of surrounding room temperature decays exponentially. And so that's interesting. That sort of follows mathematically from Newton's law of cooling, that the difference between the temperature of the object and the temperature of the surrounding room decays exponentially, like super duper fast. Okay, so unless you really want to know where our magic solutions comes from, and unless your instructor tells you otherwise, you really don't have to. You just need to know that what it is. That's enough for now, so go do something useful. Bye! Oh, come on, that is not canon. Cat videos. Oh, hi, you're still here. Okay, so let's explain where that solution comes from, or at least not exactly where it comes from. I'm going to justify to you. This is a bit of a bait and switch. Sorry. What I'm going to do is I'm going to justify to you that is the only possible solution to the equation y prime equals ky of t. Okay, so here's why y equals c times e to the kt is the only possible solution to y prime equals ky. Okay, so suppose that's true. Well, just consider, and I know so this is sort of what makes it only a justification. It doesn't really tell you where the solution comes from, but consider, for the sake of argument, the function f of t equals y of t times e to the minus kt. Why? Well, because it works as y, but you'll see. Then if we do that, then we see that f prime of t is equal to, by the product rule, the derivative of the first times the second, so that's y prime of t times e to the minus kt, plus the first times the derivative of the second, so that's y of t, plus e to the minus kt, right? The derivative of e to the something is e to the something times the chain rule factor, which is minus k. And so pulling out an e to the minus kt from both terms, we see that we have e to the minus kt times y prime of t minus ky of t. But because y is a solution to this equation, this term over here is exactly 0, and so this whole thing must be equal to 0. So we found that f prime of t is equal to 0. All right, later on we'll see that the only function that has derivative 0 is a constant, and so it must be the case that f of t is equal to some constant capital C, which means that y of t times e to the minus kt is equal to constant C. Or in other words, y of t is equal to c times e to the kt. So that was probably unsatisfying. It's not really clear where the solution y equals c times e to the kt comes from, but at least I've sort of argued to you that if you ever had any doubts, then there's no other possible solution. All right, this time for real. Goodbye!